What kind of ammunition could transform an ordinary tank gun into a weapon so devastatingly effective that soldiers who witnessed its effects spoke of it in terms usually reserved for dark magic? In the desperately innovative years of World War II, when technological advancement meant the difference between victory and annihilation, one projectile emerged that fundamentally changed armored warfare. It arrived without fanfare, without the dramatic announcements that accompanied new tank designs or aircraft models. Yet its impact on the battlefield was immediate, shocking, and so visually spectacular that even hardened veterans struggled to find adequate words to describe what they witnessed. The armored battles of the Second World War presented a constant evolutionary race. As tanks grew thicker armor, weapons needed greater penetrating power. As guns became more powerful, armor grew thicker still. This cycle drove frantic innovation on all sides, with engineers desperately seeking advantages that might tip the balance. Traditional armor-piercing ammunition, solid shot that relied on kinetic energy, and hardened steel to punch through armor plate, had reached its practical limits by the early 1940s. The thickness of armor on new German tanks was outpacing the ability of conventional projectiles to penetrate it. Allied tankers found themselves facing Tigers and Panthers, with frontal armor that could shrug off their best shots, while German guns could destroy Allied tanks at ranges where return fire proved ineffective. Into this crisis came a solution so counterintuitive, so apparently impossible, that initial reports were met with skepticism bordering on disbelief. The concept seemed to violate basic physics. Instead of a solid projectile traveling at maximum velocity, this new ammunition used a shaped charge that didn't even need to touch its target to penetrate armor. The explosive force, focused through careful engineering into a jet of superheated metal plasma, could slice through steel plate like a blowtorch through wax. Soldiers witnessing its effects for the first time spoke of German tanks melting, of armor glowing and running like liquid, of penetration so complete that entire turrets were blown off their mountings. They called it weapon witchcraft, because conventional understanding couldn't encompass what they were seeing. The Germans had a more technical term for it, Hollerdung. The Allies called it the shaped charge, and later, when refined and perfected, the high-explosive anti-tank round, forever known by its abbreviation, HEAT. The armored warfare revolution of World War II created unprecedented challenges for weapons designers. When the war began in 1939, tank armor measured in millimeters, and standard anti-tank guns could engage most targets effectively. By 1943, the situation had transformed dramatically. German tanks like the Tiger, mounted frontal armor over 100 millimeters thick, carefully sloped and hardened to maximize protection. The Panther, perhaps the best overall tank design of the war, combined thick armor with excellent ballistic shaping that caused shells to deflect rather than penetrate. Allied tankers in Shermans, equipped with the standard 75mm gun-firing conventional armor-piercing ammunition, found themselves catastrophically outmatched. The problem was fundamentally one of physics and metallurgy. Traditional armor-piercing ammunition depended on kinetic energy, mass times velocity squared, to penetrate armor. A dense, hardened projectile traveling at high velocity struck armor plate, and if the projectile was hard enough and fast enough, punched through. This approach worked adequately against early war tanks, but it faced inherent limitations. Increasing projectile velocity required larger guns with longer barrels and more powerful propellant charges, making weapons heavier and more difficult to mount in tanks or field positions. Increasing projectile mass reduced velocity and limited range. Meanwhile, armor plate could be made thicker, harder, and better shaped to deflect incoming rounds. The Germans initially held advantages in this arms race. Their experience in the Spanish Civil War and early campaigns had convinced them of armor's importance. They developed the Tiger I tank specifically to overmatch any opponent, mounting the fearsome 88mm gun that could destroy any Allied tank at ranges exceeding 2,000 yards. The Panther, introduced in 1943, combined the 75mm KWK-42 gun with thick, well-sloped armor that made frontal penetration extremely difficult. These vehicles represented engineering excellence applied to battlefield dominance, and they gave German armored units qualitative superiority that compensated partly for their increasing numerical inferiority. Allied responses initially focused on conventional solutions. The British developed more powerful anti-tank guns, like the excellent 17-pounder, which could engage German heavy tanks effectively, but remained difficult to mount in existing tank designs. The Americans upgunned some Sherman tanks with 76mm weapons that improved penetration, but still left crews vulnerable against German heavy armor. The Soviets produced the T-34-85, mounting an 85mm gun that provided better offensive capability. These improvements helped, but they represented incremental advances in an evolutionary race where the Germans maintained their lead through superior metallurgy and engineering. The shaped charge principle offered a revolutionary alternative, first discovered in the late 19th century and refined in the 1930s by researchers, including Swiss physicist Henry Mohaupt and German ordnance engineers. The shaped charge exploited a phenomenon that seemed almost magical. A hollow cone of explosive, when detonated, focused the explosive force into a jet of superheated gas and molten metal that could penetrate armor far thicker than conventional projectiles. The penetration did not depend on the projectile's velocity, meaning shaped charges could work from weapons with relatively low muzzle velocities. They could even function in handheld weapons, opening possibilities for infantry anti-tank capabilities previously impossible. The physics behind shaped charges challenged intuition. The hollow cone, lined with metal, collapsed inward when the surrounding explosive detonated. The liner material, typically copper or steel, was compressed and accelerated to extreme velocities, forming a jet that traveled at speeds exceeding 20,000 feet per second. This jet, though comprising only a small amount of material, carried enormous kinetic energy concentrated in a tiny area. When it struck armor, the combination of extreme velocity and focused energy overwhelmed the metal's structural integrity. The armor didn't simply break, it flowed and sprayed away as the jet punched through, creating a narrow penetration channel, but depositing tremendous energy inside the target vehicle. Germany pioneered military applications of shaped charge technology, developing handheld weapons like the Panzerfaust and Panzerschreck that gave infantry formidable anti-tank capability. These weapons transformed infantry tactics, making even the most powerful tank vulnerable to determined foot soldiers. The psychological impact was profound. Tank crews, previously confident in their armor's protection against anything but direct hits from large-caliber guns, now faced threats from soldiers hiding in rubble with weapons that could kill at close range. The Allies initially struggled to develop equivalent capabilities. British and American researchers understood the shaped charge principle, but translating theory into reliable munitions proved challenging. Early attempts produced inconsistent results. Some rounds penetrated impressively, others barely scratched armor. The problem lay in manufacturing precision. The shaped charge was extraordinarily sensitive to imperfections. If the cone wasn't perfectly symmetrical, if the explosive didn't detonate uniformly, if the standoff distance wasn't correct, penetration suffered dramatically. Achieving the necessary precision in mass production under wartime conditions with less than ideal materials required solving numerous technical challenges. By 1943, both sides were deploying shaped charge ammunition with increasing effectiveness. The Germans used heat rounds in their tank guns and developed specialized weapons like the Steel Granite 41, a massive shaped charge grenade that could be fired from standard infantry howitzers. The Allies developed the Projector Infantry Anti-Tank, better known as the Piat, a British spring-loaded weapon that fired shaped charge projectiles. More significantly, they began fielding heat rounds for tank guns and anti-tank weapons, giving their forces tools that could engage German armor more effectively. The tactical implications were enormous. Shaped charges democratized anti-tank warfare. A bazooka team properly positioned could destroy a Tiger that might otherwise rampage through an entire company. A Sherman tank, despite its inferior gun, could threaten Panthers if it could get close enough to use heat ammunition effectively. The shaped charge didn't eliminate German armored superiority, but it narrowed the gap significantly. More importantly, it changed how battles were fought. Tank tactics evolved to emphasize avoiding situations where infantry could approach close enough to use shaped charge weapons. Defensive positions incorporated standoff distances that reduced heat effectiveness. The entire tactical environment shifted in response to this new technology. The development of heat ammunition also reflected the war's broader technological competition. Both sides fielded brilliant scientists and engineers who worked frantically to gain advantages. The shaped charge represented applied physics at its most practical, theoretical knowledge, transformed into battlefield weapons. The scientists who refined shaped charge technology probably never witnessed its effects personally, yet their calculations and experiments produced weapons that soldiers described in terms approaching the supernatural. This disconnect between laboratory and battlefield, between theoretical understanding and visceral reality, characterized much of World War II's technological warfare. When Allied Supreme Commander General Dwight Eisenhower reviewed intelligence reports about German shaped charge weapons in late 1943, he recognized their significance immediately. The reports described Panzerfaust attacks that had destroyed American tanks with single hits, something that shouldn't have been possible from handheld weapons. Eisenhower ordered accelerated development and production of Allied-shaped charge weapons, understanding that matching this capability was essential. His intervention reflected how shaped charges had elevated from technical curiosity to strategic concern at the highest command levels. The industrial mobilization required to produce shaped charge ammunition in quantities sufficient for modern warfare strained even the most capable economies. The United States, with its vast manufacturing capacity, eventually produced millions of heat rounds and bazookas. Britain manufactured hundreds of thousands of Piat rounds and developed heat ammunition for various guns. Germany, despite increasing resource constraints, maintained production of Panzerfausts and Panzerschrecks through 1945, prioritizing these weapons as force multipliers for their shrinking armies. The Soviet Union, though slower to adopt shaped charge technology broadly, eventually fielded its own versions as the war progressed. The intelligence war surrounding shaped charge technology added another dimension to their development. Both sides sought information about enemy capabilities while protecting their own secrets. German intelligence tried to determine Allied shaped charge effectiveness and production capacity. Allied intelligence tracked German developments, captured examples when possible, and analyzed them to understand construction and capabilities. This intelligence competition influenced tactical decisions, as commanders adjusted plans based on what they knew or believed about enemy-shaped charge weapons. The shaped charge's journey from laboratory curiosity to battlefield weapon spanned decades and involved researchers across multiple nations, none of whom initially grasped the military implications of their discoveries. The story began in 1888 when American scientist Charles Edward Munro discovered an unusual phenomenon while experimenting with explosive charges. He noticed that when explosive blocks with letters embossed on one surface were detonated against steel plates, the letters appeared in relief on the metal. The explosive had somehow focused its energy, creating an effect far more concentrated than uniform detonation should produce. Munro's discovery, which became known as the Munro effect, remained a scientific curiosity for decades. He published his findings. Other researchers confirmed the phenomenon, but no one immediately saw practical applications. The idea that explosive force could be shaped and directed contradicted conventional understanding of explosives, which were thought to produce uniform blast effects. Military explosive ordnance of the period relied on blast and fragmentation, not focused penetration. The shaped charge awaited further development and the recognition of its potential. The breakthrough came in the 1930s, through parallel research in several countries. In Germany, military researchers experimenting with hollow charge designs found they could achieve remarkable penetration of armor plate. Franz Rudolf Tomanek, working for the German Army's Ordnance Department, developed practical applications, creating designs that would evolve into wartime weapons. His work remained classified, but it gave Germany a significant head start in shaped charge technology when war began. Simultaneously, Swiss physicist Henry Mohaupt conducted research that reached similar conclusions through different approaches. Mohaupt recognized that the hollow cone shape was critical to focusing explosive energy. He refined the geometry, determining optimal angles and dimensions for maximum penetration. His work attracted military attention, and he eventually brought his expertise to Britain and later the United States, where it influenced Allied-shaped charge development. Mohaupt's contributions to the Allied war effort, though less celebrated than those of some scientists, proved enormously valuable. His theoretical understanding and practical experience accelerated Allied programs significantly. The physics underlying the shaped charge effect involved complex fluid dynamics that weren't fully understood until later. When the explosive surrounding the hollow cone detonated, a detonation wave traveled through it at several thousand meters per second. This wave compressed the metal liner of the cone, collapsing it inward. The liner material, subjected to enormous pressures, behaved not as a solid but as a fluid, flowing and accelerating to extreme velocities. The collapse progressed from the open end of the cone toward the apex, with material from the liner forming a high-velocity jet and a slower-moving slug. The jet was the penetrating mechanism. Traveling at hypersonic velocities and focused into a narrow stream, it carried tremendous kinetic energy per unit area. When this jet struck armor, the combination of extreme velocity and focused energy created pressures far exceeding the armor's yield strength. The armor responded by flowing out of the way, behaving more like a viscous fluid than a solid material. This process, called hydrodynamic penetration, didn't depend on the hardness or strength of the penetrator or target in the conventional sense. It depended on density and velocity, which meant that shaped charges could penetrate armor far thicker than the jet itself. Understanding this mechanism required sophisticated mathematical modeling and experimental validation. Researchers used high-speed photography to capture jet formation, though cameras of the era struggled to record events happening in microseconds. They conducted metallurgical analysis of penetrated armor to understand how material responded to shaped charge attack. They built mathematical models based on fluid dynamics equations normally applied to liquids, not solids, because armor behaved as fluid under the extreme conditions shaped charges created. This interdisciplinary work, combining physics, mathematics, metallurgy, and engineering, represented science at its most rigorous, applied to military problems. Early military applications focused on demolitions rather than anti-tank weapons. Hollow charge explosives proved excellent for cutting steel structures, clearing obstacles, and breaching fortifications. German engineers used shaped charges for demolition work, developing increasingly sophisticated designs. The progression from demolition tools to anti-tank weapons required recognizing that the same physics that cut through steel beams could penetrate armor plate. This conceptual leap, obvious in retrospect, represented significant innovation at the time when roles for different weapon types were rigidly defined. The Germans fielded the first handheld shaped charge anti-tank weapons. The Panzerfaust, developed in 1942, consisted of a disposable tube containing a shaped charge warhead. Simple and cheap to manufacture, it could be produced in enormous quantities and issued widely to infantry. The weapon's effective range was limited to about 60 meters, but at that distance, its shaped charge could penetrate 140 millimeters of armor, enough to defeat any Allied tank. The Panzerfaust transformed German infantry into a credible anti-tank force, even as Germany's armored formations declined in strength. The weapon's design reflected German engineering pragmatism. The tube was simple steel, the trigger mechanism basic but reliable. The warhead used a crude but effective shaped charge design that sacrificed optimal performance for ease of manufacture. Most ingeniously, the weapon was disposable, eliminating complexity of reloading mechanisms and reducing cost. A soldier could carry multiple Panzerfausts, engage tanks, and discard the used tubes. This design philosophy, prioritizing quantity and ease of production over refinement, suited Germany's late-war circumstances, where industrial capacity was stretched thin. The Panzerschreck, a reusable tube-launched weapon similar to the American bazooka, but more powerful, followed. Its shaped charge warhead could penetrate even thicker armor, threatening all Allied tanks. These weapons appeared on the eastern and western fronts in growing numbers from 1943 onward, forcing Allied armor tactics to adapt. Tank units learned to avoid urban areas where infantry with shaped charge weapons could attack from close range. Infantry support became essential to suppress Panzerfaust teams before they could engage tanks. The mere presence of these weapons influenced tactical decisions, even when they weren't actually employed. Allied development followed different paths initially. The British Piat, introduced in 1942, used a spring mechanism to launch shaped charge projectiles. While effective, it was heavy, difficult to cock, and had limited range. The weapon gained a reputation among troops as being awkward and unreliable, though in skilled hands, it could destroy any tank. American bazooka development progressed through several iterations, with each version improving penetration and reliability. The M9A1 bazooka, introduced in 1943, represented mature design that balanced effectiveness against practicality. These weapons gave Allied infantry their own anti-tank capabilities, partially addressing the disadvantage they faced against German armor. The development of shaped charge ammunition for tank guns and artillery presented greater challenges than handheld weapons. The projectile needed to survive the extreme acceleration of gun launch without damaging the precisely shaped cone. It needed to remain stable in flight, despite unusual weight distribution. Most critically, it needed to function reliably at the optimal standoff distance from the target. If the shaped charge detonated too close to armor or too far away, penetration suffered dramatically. Solving these problems required extensive testing and refinement. Engineers developed projectiles with carefully designed fuses that ensured detonation at the correct distance. They created cone geometries that balanced penetration against manufacturing practicality. They selected liner materials that optimized jet formation. This work progressed through 1943 and 1944, with both sides fielding increasingly effective shaped charge ammunition for their weapons. The iterative process of design, testing, modification, and retesting consumed enormous resources and time, but it was essential to producing weapons that worked reliably under combat conditions. The M67 heat round for the American 90mm gun, introduced in 1944, exemplified mature shaped charge design. It could penetrate approximately 100mm of armor, making it effective against most German tanks if it hit in the right location. The round incorporated sophisticated fusing, aerodynamic stabilization, and a carefully optimized shaped charge. Similar developments occurred in other nations' ordnance programs. The Germans fielded heat rounds for their tank guns, though they often preferred conventional armor-piercing ammunition when range allowed. The Soviets developed shaped charge ammunition for their guns, though they tended to rely more on massed armor and superior numbers than technological sophistication. The production of shaped charge ammunition required precision manufacturing that challenged wartime industrial capabilities. The metal cone needed to be formed to exacting tolerances. The explosive filling required careful handling and uniform density. The fuse mechanisms needed to function reliably under combat conditions. Quality control was essential, as defective rounds might fail to penetrate when soldiers' lives depended on them. Despite these challenges, production ramped up, and by late 1944, shaped charge ammunition was available in substantial quantities to Allied forces. Testing shaped charge ammunition involved both controlled laboratory experiments and field trials that sometimes produced unexpected results. Test ranges featured captured German tanks as targets, allowing engineers to evaluate penetration against actual armor. High-speed cameras recorded jet formation and penetration events, providing data for refining designs. Metallurgical analysis of penetrated armor revealed how different shaped charge designs affected targets. This systematic approach to weapons development, combining theoretical knowledge with empirical testing, represented modern military research methodology at its most effective. The visual effects of shaped charge penetration shocked everyone who witnessed them. Unlike conventional armor-piercing rounds that punch neat holes, shaped charges created dramatically different damage patterns. The jet bored through armor with such intensity that metal around the penetration point melted and glowed. Inside the target vehicle, the jet and fragments created a storm of destruction, igniting ammunition, fuel, and killing crew members. Secondary explosions often followed as onboard ammunition cooked off. Tanks hit by shaped charges didn't just stop, they burned, their ammunition exploding in spectacular fashion. This visible effectiveness convinced soldiers of the weapon's power, earning it the reputation that led to descriptions invoking witchcraft and supernatural power. Combat use revealed both the effectiveness and limitations of shaped charge weapons. When conditions were right, properly positioned operators could destroy tanks with single hits, yet many attacks failed due to misses, deflections off angled armor, or rounds that failed to detonate properly. The shaped charge was powerful but not infallible, and its effectiveness depended heavily on tactical employment and operator skill. Experienced troops learned to maximize advantages while minimizing limitations, using shaped charges as part of combined arms operations rather than relying on them exclusively. The psychological warfare dimension of shaped charges deserves mention. Both sides used propaganda about these weapons to influence enemy morale. Germans emphasized their Panzerfaust's effectiveness in training materials and propaganda, encouraging soldiers that they could defeat enemy armor. Allies highlighted their own shaped charge weapons to reassure troops facing superior German tanks. The weapon's dramatic visual effects made them excellent propaganda subjects, as photographs and film footage of destroyed tanks convinced audiences of their power. This psychological dimension extended shaped charges' influence beyond their actual battlefield impact. The shaped charge revolution in anti-tank warfare embodied several themes that extended beyond mere military technology. Understanding these concepts provides insight into how warfare evolves and how technological innovation interacts with tactical, strategic, and psychological dimensions of combat. The democratization of anti-tank capabilities represented the shaped charge's most significant impact. Before heat ammunition became available, destroying tanks required other tanks or large, specialized anti-tank guns. These weapons were expensive, difficult to produce, and required extensive training to employ effectively. The shaped charge changed this equation fundamentally. A single infantryman with a Panzerfaust or bazooka could destroy the most expensive, technically sophisticated tank on the battlefield. The soldier required only basic training, and the weapon cost a tiny fraction of the tank's price. This inverted the economic and tactical calculations that had governed armored warfare. This democratization had profound implications. Tank supremacy, which had defined early World War II operations, became increasingly difficult to maintain. The blitzkrieg tactics that had conquered Poland and France relied on tanks operating relatively freely once they penetrated enemy lines. By 1944, such operations faced constant threat from shaped charge weapons. Every building might conceal a Panzerfaust team. Every hedgerow could hide a bazooka operator. Tanks required infantry support to survive, and operations in urban terrain became extraordinarily hazardous. The shaped charge didn't eliminate the tank's value, but it constrained how tanks could be employed and made armored operations more costly and complex. The economic implications extended to strategic planning. Military planners recognized that shaped charges allowed defenders to inflict disproportionate losses on attackers. A defending force armed with shaped charge weapons could destroy armor at relatively low cost, creating favorable exchange ratios that complicated offensive operations. This affected decisions about force structure, with armies needing to balance expensive armored units against the risk they faced from cheap weapons. The calculation became more complex, and the advantages of numerical armored superiority less decisive. The shaped charge also represented the triumph of physics over brute force. Conventional anti-tank weapons relied on straightforward concepts: larger guns, faster projectiles, harder penetrators. The arms race involved making everything bigger and more powerful. Shaped charges bypassed this competition through clever application of physical principles. A relatively small explosive charge, properly shaped and positioned, could defeat armor that would resist much larger conventional projectiles. This represented a different approach to military problems, one that emphasized understanding physical phenomena and exploiting them cleverly rather than simply scaling up existing solutions. This intellectual approach to weapons development reflected broader trends in mid-20th century warfare. Scientific understanding increasingly provided military advantages. Nations with strong research establishments and cultures that valued scientific education gained edges in weapons development. The shaped charge exemplified how theoretical physics could be weaponized through engineering, creating capabilities that brute industrial might alone could not achieve. This presaged the increasing role of science and technology in military competition that would characterize the Cold War and subsequent conflicts. The counterintuitive nature of shaped charges challenges conventional military thinking in instructive ways. Military organizations tend toward conservatism, preferring proven methods over untested innovations. The shaped charge seemed impossible to officers educated in traditional ballistics and armor penetration. A projectile that didn't need high velocity to penetrate armor, an explosive that could penetrate more effectively than solid shot. These concepts contradicted established doctrine and experience. Yet they worked, and worked spectacularly. The shaped charge's success demonstrated that warfare rewards innovation, and that conventional wisdom sometimes obscures revolutionary possibilities. This lesson about the value of challenging assumptions remained relevant long after World War II. Military establishments that remained open to unconventional ideas gained advantages over those bound by tradition. The shaped charge became a case study in how innovation occurs in large conservative organizations and what conditions enable revolutionary developments. The fact that multiple nations developed shaped charges independently suggested that when conditions were right, innovation occurred despite organizational conservatism, though organizations that actively encouraged innovation generally progressed faster. Manufacturing precision emerged as a critical factor in shaped charge effectiveness. Unlike conventional ammunition, where minor variations in production rarely affected performance significantly, shaped charges were extraordinarily sensitive to imperfections. A cone that was slightly asymmetric, explosive that wasn't perfectly uniform, a fuse that functioned incorrectly. Any of these defects could reduce penetration dramatically or cause complete failure. This meant that mass production of effective shaped charge ammunition required maintaining precision that challenged wartime manufacturing capabilities. This tension between the need for mass production and requirement for precision reflected broader challenges of industrial warfare. Modern military technology increasingly demanded both quantity and quality. Armies needed thousands of rounds, but those rounds needed to work reliably. Achieving this combination required sophisticated quality control, skilled workers, and manufacturing processes that balanced speed against precision. The nations that managed this balance most effectively gained significant advantages. The Germans, despite their engineering sophistication, sometimes struggled to maintain quality while meeting quantity demands. The Americans, with their industrial capacity and emphasis on standardization, eventually achieved both goals, producing shaped charge ammunition that worked reliably in large quantities. The challenge of maintaining quality under pressure revealed vulnerabilities in different national industrial systems. German industry, increasingly disrupted by Allied bombing and resource shortages, struggled to maintain precision manufacturing. Quality variations in late-war German shaped charge ammunition reflected these constraints, with some batches performing well and others showing high failure rates. Allied industry, operating with secure supply lines and abundant resources, maintained more consistent quality. This industrial dimension of military effectiveness often received less attention than battlefield tactics, but proved equally important to outcomes. The psychological impact of shaped charges deserves particular attention. Weapons that produce visually dramatic effects exert psychological influence beyond their actual lethality. The shaped charge's ability to make armor glow and melt, to create spectacular secondary explosions, to utterly destroy vehicles in moments, all created powerful psychological effects. Soldiers who witnessed these effects spoke of them with awe and dread. Tank crews facing shaped charge weapons experienced fear that went beyond rational calculation of risk. The knowledge that their armor might not protect them, that a single hit could transform their vehicle into an inferno, affected morale and tactical decision-making. This psychological dimension extended to how soldiers described shaped charge effects. The recurring references to melting, to armor running like liquid, to supernatural or magical qualities, all reflected attempts to process and communicate experiences that defied everyday reference points. Most soldiers had never seen metal behave like the armor struck by shaped charges. Their descriptions reached for metaphors that conveyed the uncanny quality of what they witnessed. The term weapon witchcraft captured this sense of something beyond normal understanding, an effect that seemed to violate natural law. The language soldiers used revealed their struggle to comprehend what they experienced. Combat veterans, accustomed to violence and destruction, were nonetheless shocked by shaped charge effects. Their descriptions emphasized transformation, armor changing state from solid to liquid, vehicles changing from machines to pyres. This transformational quality, the dramatic alteration of matter's state, carried almost alchemical connotations. The shaped charge made soldiers witnesses to physics at extremes, where materials behaved in ways that contradicted everyday experience. The shaped charge also illustrated the feedback loop between offensive and defensive technology. Each advance in penetrating power prompted advances in protection, which prompted further offensive developments. Tankers learned to avoid situations where infantry could employ shaped charges effectively. Engineers developed standoff armor, mesh screens positioned away from hull that detonated shaped charges prematurely, reducing their effectiveness. Later designs incorporated reactive armor that exploded outward when struck, disrupting the jet formation. These countermeasures worked to varying degrees, but they represented the continuing evolution that characterized armored warfare technology. This evolutionary dynamic between weapon and protection has characterized military technology throughout history. Armor prompted better weapons, which prompted better armor, in cycles stretching back to ancient times. The shaped charge represented one turn in this eternal wheel, though a particularly significant one. The responses it provoked, from standoff armor to reactive armor to eventual composite armor, shaped tank design for decades. Understanding this dynamic helps explain why revolutionary weapons rarely remain revolutionary for long, as adversaries develop countermeasures that restore some balance. The strategic implications of widespread shaped charge availability affected force structure and doctrine. Armies needed to consider that their expensive armored units faced significant vulnerability to cheap weapons wielded by ordinary infantry. This influenced decisions about how many tanks to produce, what kind of support they required, and how to employ them tactically. It also influenced infantry doctrine, as armies recognized that properly equipped and trained infantry could control terrain even against armored forces. The shaped charge thus affected not just tactics, but operational art and strategic planning. These strategic considerations played out differently in different armies. The Germans, facing resource constraints and fighting defensively, emphasized shaped charge weapons as force multipliers that allowed outnumbered forces to inflict heavy losses on attackers. The Americans, with industrial superiority and offensive missions, accepted shaped charge threats as manageable risks given their numerical advantages. The Soviets, prioritizing mass over sophistication, developed shaped charge weapons but relied more on overwhelming numbers of tanks than on technological parity. These different approaches reflected how the same technology could be integrated differently based on national circumstances and strategic situations. The role of scientific expertise in weapons development illustrated the increasingly technical nature of modern warfare. Shaped charges required understanding complex physics that was far beyond normal ordnance engineering. The specialists who developed these weapons needed university-level education in physics and engineering. Their work couldn't be accomplished through traditional craftsmanship or incremental improvement of existing designs. It required theoretical understanding and experimental validation of complex phenomena. This represented warfare's evolution toward increased dependence on scientific and technical expertise, a trend that has only accelerated in subsequent decades. The mobilization of scientific talent for weapons development during World War II created institutional structures and relationships between academia, industry, and military that persisted after the war. Research universities became centers for weapons development. Government laboratories expanded dramatically. Industrial research facilities contributed to military projects. This military-industrial academic complex, though the term wasn't coined until later, emerged from wartime necessity and shaped subsequent technological development for decades. The shaped charge was one product of this system, but the system itself proved more consequential than any individual weapon. The shaped charge's development across multiple nations simultaneously demonstrated how scientific knowledge transcends national boundaries even during wartime. The basic physics was understood by researchers in Germany, Switzerland, Britain, and the United States. While specific applications remained classified, the underlying principles were part of international scientific literature. This meant that once one nation fielded shaped charge weapons, others could develop their own versions relatively quickly. Scientific knowledge, unlike specific manufacturing techniques or tactical innovations, proved difficult to monopolize. This international dimension of scientific knowledge created interesting dynamics during the war. Scientists who had collaborated in peacetime found themselves working for opposing nations. Published research from the 1930s informed weapons development on both sides. Captured weapons and documents accelerated programs by revealing what adversaries had achieved. The scientific community's international character meant that advantages from research could be temporary unless protected through secrecy or rapid translation into deployed weapons that adversaries couldn't easily copy. The shaped charge presented both a solution to the problem of defeating thick armor and new problems that required innovative solutions. Understanding how engineers and tacticians addressed these challenges illuminates the creative problem-solving that characterized World War II's technological competition. The fundamental solution the shaped charge provided was defeating armor without requiring ever larger guns. By the mid-war period, the trend toward bigger guns was reaching practical limits. The German 88mm and Soviet 122mm guns were approaching the maximum size that could be mounted in mobile weapons. Larger calibers would require vehicles too heavy to move effectively or gun systems too cumbersome for tactical flexibility. The shaped charge broke this trajectory by achieving penetration through physics rather than kinetic energy. A 75mm heat round could penetrate armor that would resist 75mm conventional ammunition, effectively increasing gun capability without increasing gun size. This solution enabled smaller vehicles to carry effective anti-tank weapons. The American bazooka, weighing barely 15 pounds, could threaten any tank. The German Panzerfaust, even lighter and simpler, gave every infantryman anti-tank capability. This meant that infantry units could defend against armor without requiring organic anti-tank guns, reducing their logistical burden and increasing tactical flexibility. Infantry could operate independently in situations where they would previously have needed armor or heavy weapons support. The implications for force structure were significant. Divisions could be lighter and more mobile if they didn't need to incorporate heavy anti-tank guns. Supply requirements decreased when anti-tank capability came from weapons that weighed pounds instead of tons. This allowed more flexible organization and deployment, as units weren't tied to road networks capable of moving heavy guns. The tactical and operational flexibility this provided influenced how armies organized and employed forces throughout the war's later phases. The manufacturing challenge posed by shaped charges prompted ingenious solutions. The precision required for the cone seemed to demand machining that was too expensive and time-consuming for mass production. Engineers solved this through pressing and forming techniques that achieved necessary precision more economically. Metal spinning, die forming, and careful quality control produced cones that met specifications while allowing production in large quantities. The explosive filling used carefully formulated compositions that flowed into cavities uniformly and provided consistent detonation characteristics. These manufacturing innovations transformed shaped charges from laboratory devices into practical munitions producible in millions of units. The development of these manufacturing processes represented significant engineering achievement. Creating dies that could form cones to required tolerances demanded precision tool-making. Developing explosive formulations that were both safe to handle and consistent in performance required extensive testing. Establishing quality control procedures that could identify defective rounds without slowing production necessitated innovation in inspection techniques. The cumulative effect of these manufacturing advances enabled shaped charge production at scales sufficient for modern warfare. Worker training became crucial as shaped charge production expanded. The weapon's sensitivity to manufacturing defects meant that workers needed to understand why precision mattered and how to achieve it. Training programs emphasized quality over speed, teaching workers to identify potential problems before they resulted in defective ammunition. This represented a shift from traditional munitions manufacturing, where tolerances were less critical and production speed was emphasized more heavily. The human dimension of manufacturing quality proved as important as the machinery and processes employed. The standoff distance problem, ensuring detonation at the optimal distance from target armor, required creative fusing solutions. Early shaped charges sometimes detonated on contact before the optimal standoff was achieved. Engineers developed fuses with extended probes that ensured correct detonation distance. The German Panzerfaust used a simple wooden block that held the warhead at the proper distance. Tank-fired heat rounds incorporated base detonating fuses designed to function at precisely the right moment. These solutions balanced reliability, cost, and effectiveness, producing weapons that functioned consistently under combat conditions. Fuse development involved solving multiple competing requirements. The fuse needed to survive gun launch without damage. It needed to arm safely, preventing accidental detonation. It needed to function reliably when striking targets at various angles and velocities. It needed to detonate the shaped charge at optimal standoff despite these variations. Meeting all these requirements simultaneously required careful design and extensive testing. The fuses that emerged represented compromise between ideal performance and practical reliability, but they worked well enough to make shaped charges effective battlefield weapons. Stabilizing shaped charge projectiles in flight presented unique challenges. The hollow cone created unusual weight distribution that could cause instability. Some designs used fins for stabilization, similar to arrows. Others relied on careful balancing and ballistic shaping. Tank-fired heat rounds often incorporated both rotational stabilization from rifling and aerodynamic features that maintained stability. These solutions allowed shaped charges to be delivered accurately enough for battlefield use despite their unconventional geometry. The aerodynamics of shaped charge projectiles required understanding not available from conventional ammunition design. Wind tunnel testing, though limited by wartime constraints, helped refine shapes. Mathematical modeling, based on emerging computer capabilities, informed design decisions. Field testing validated designs under operational conditions. This combination of theoretical understanding, experimental investigation, and practical testing represented sophisticated engineering practice applied to weapons development. The success of these efforts enabled shaped charges to function reliably in combat, translating laboratory potential into battlefield effectiveness. The solution to protecting tanks against shaped charges evolved through several iterations. Early attempts involved increasing armor thickness, but this proved ineffective. The shaped charge's penetration didn't depend on projectile kinetic energy, so thicker armor provided limited additional protection unless it was far thicker than practical. Engineers developed standoff armor, screens, or skirts positioned away from the hull that detonated shaped charges prematurely. By forcing detonation before the jet fully formed, or at incorrect standoff distance, these screens reduced penetration significantly. German tanks increasingly featured such protection, particularly on their vulnerable sides. Standoff armor represented an elegant solution to shaped charge threats. Rather than trying to resist penetration directly, it disrupted the mechanism by which shaped charges worked. This approach, defeating weapons by interfering with their functioning rather than resisting their effects, became increasingly common in military technology. Active protection systems, electronic countermeasures, and various defensive technologies employ similar principles. The shaped charge thus influenced not just armor design, but broader conceptual approaches to protection. Reactive armor represented a more sophisticated solution developed later. This consisted of explosive blocks mounted on vehicle surfaces. When struck by a shaped charge jet, the reactive armor exploded outward, disrupting jet formation and reducing penetration. While reactive armor saw limited use during World War II, it became standard on later armored vehicles. Its development illustrated the continuing evolution of protection against shaped charge threats. The competition between shaped charge weapons and armor protection continues today, with both technologies advancing in response to each other. Tactical solutions complemented technological responses. Tank tactics evolved to minimize exposure to shaped charge weapons. Vehicles avoided urban terrain, where infantry with short-range weapons could approach closely. They operated with infantry support that could suppress or eliminate shaped charge teams before they could fire. Commanders emphasized maintaining standoff distances that put tanks beyond the effective range of handheld shaped charge weapons while allowing their own guns to engage. These tactical adaptations reduced vulnerability without requiring technological solutions. The integration of infantry and armor became closer as shaped charge threats increased. Tank units that had operated relatively independently early in the war increasingly required infantry support. Infantry learned to screen tanks from shaped charge attacks, suppressing enemy infantry before they could employ anti-tank weapons. This combined arms approach, though it reduced operational tempo compared to pure armor operations, proved necessary for survival. The tactical doctrine that emerged from this experience shaped how armies employed armor for decades after the war. Infantry tactics for employing shaped charges emphasized surprise and concealment. Panzerfaust teams learned to wait until tanks were within effective range before revealing their positions. They targeted vulnerable aspects of tanks, particularly sides and rear, where armor was thinner. They worked in pairs or teams, with one soldier engaging while others provided security or backup. These tactics maximized the shaped charge's effectiveness despite limitations in range and the single-shot nature of many weapons. The tactical innovation required to employ shaped charges effectively paralleled the technical innovation that created them. Urban combat tactics evolved specifically around shaped charge employment. Buildings provided concealment for infantry armed with these weapons. Upper floors offered firing positions down onto tank-top armor. Rubble and debris created obstacles that slowed tanks, allowing shaped charge teams time to engage. These characteristics made cities extremely dangerous for armor, fundamentally changing how urban warfare was conducted. Tanks that had been dominant in open terrain became vulnerable in built-up areas, requiring extensive infantry support and specialized tactics to survive. The integration of shaped charge ammunition into existing weapon systems required solving compatibility problems. Heat rounds needed to function in guns designed for conventional ammunition. They needed to survive the launch stress without damage to the precisely shaped cone. They needed to be stable enough for field storage and handling. Engineers achieved this through careful design that balanced shaped charge requirements against practical constraints. The result was ammunition that could be issued to existing units and used with existing weapons without requiring extensive retraining or new equipment. This compatibility consideration influenced design throughout shaped charge development. Ammunition needed to fit existing supply chains and storage systems. It needed to be handled by soldiers with training for conventional ammunition. It needed to work with existing loading equipment and procedures. Meeting these constraints while achieving effective shaped charge performance required compromises that sometimes reduced theoretical maximum effectiveness but ensured practical battlefield utility. The balance between optimal performance and practical usability characterized much of wartime weapons development. The solution to the shaped charge's reduced effectiveness against sloped armor involved improved designs. Early shaped charges were less effective against armor positioned at steep angles. Engineers developed asymmetric liner designs and modified cone geometries that maintained penetration against sloped armor. These improvements required sophisticated understanding of jet formation dynamics and extensive testing, but they produced shaped charges that worked effectively against the sloped armor common on late war tanks. The continuing refinement of shaped charge technology illustrated how weapons evolve through cycles of use, evaluation, and improvement. Advanced shaped charge designs incorporated multiple improvements simultaneously. Better explosive compositions provided more consistent detonation. Refined cone geometries optimized jet formation. Improved liner materials enhanced penetration. These cumulative advances produced weapons significantly more effective than early versions. The evolutionary development of shaped charges illustrated how military technology progresses through incremental improvements that accumulate into substantial advances. Each generation of shaped charge represented lessons learned from previous versions, creating a trajectory of continuous improvement throughout the war. Logistics solutions addressed the challenge of distributing specialized ammunition to units that needed it. Heat rounds, being more complex than conventional ammunition, couldn't be produced as quickly or cheaply. Supply systems needed to ensure that units facing heavy armor received priority allocation. This required intelligence about enemy armor dispositions and flexible logistics that could adjust distribution as situations evolved. The Allies developed systems that tracked ammunition types and managed distribution to ensure that shaped charge ammunition reached units where it would be most valuable. The logistics of shaped charge weapons extended beyond simple distribution. Storage required protection from moisture and temperature extremes that could degrade explosives. Transportation needed to prevent damage to precisely shaped cones. Issue procedures needed to ensure soldiers received functional ammunition. These logistics considerations influenced everything from packaging design to storage facility requirements. The attention to logistics details, though less dramatic than battlefield performance, proved essential to translating manufacturing capability into combat effectiveness. Training solutions addressed the need to familiarize soldiers with shaped charge weapons and ammunition. These weapons operated differently from conventional firearms and required understanding unique characteristics. Training programs taught soldiers about optimal engagement ranges, aiming techniques, and proper employment tactics. For tank-fired heat ammunition, gunners learned how shaped charges differed from conventional rounds in trajectory and effective range. This training ensured that soldiers could employ shaped charge weapons effectively, maximizing their combat value. Effective training programs combined classroom instruction with practical exercises. Soldiers learned theory of shaped charge operation, though usually in simplified terms appropriate to their educational backgrounds. They practiced with inert training rounds, to develop muscle memory for loading and firing. When possible, they observed live demonstrations that showed shaped charge effects. This combination of theoretical knowledge, practical skill development, and visual reinforcement produced soldiers capable of employing shaped charges confidently and effectively under combat conditions. The shaped charge's revolutionary impact on armored warfare invites reflection on its limitations, the responses it provoked, and its broader implications for military technology and tactics. Understanding these dimensions provides balanced perspective on this transformative weapon. The shaped charge's effectiveness, while impressive, came with significant limitations that often went unmentioned in dramatic accounts. Effective range was considerably less than conventional anti-tank guns. A Panzerfaust worked at 60 meters, a bazooka at perhaps 150 meters. Tank-fired heat rounds had longer range, but still less than conventional armor-piercing ammunition. This range limitation meant that shaped charge weapons required users to close with targets, accepting risk to achieve effective firing positions. In open terrain, this could be extraordinarily difficult against opponents with superior observation and long-range weapons. This range limitation created tactical dilemmas. Infantry armed with shaped charges needed to approach within effective range, often crossing open ground under fire. Tank crews needed to maneuver closer to targets than they would prefer, accepting vulnerability to achieve effective firing positions. These tactical challenges meant that shaped charges, though powerful, couldn't be employed casually. They required careful planning, favorable terrain, and often considerable courage from users. The weapon's power was real, but accessing that power required accepting significant risks. Accuracy presented another challenge, particularly for handheld weapons. The Panzerfaust was notoriously inaccurate beyond point-blank range. Wind affected lightweight projectiles significantly. The shaped charge's effectiveness depended on striking the target squarely, not at oblique angles. These factors meant that even when operators achieved firing positions, successful hits required skill and often luck. Many shaped charge attacks missed or struck at angles that reduced penetration, allowing tanks to survive and retaliate. Combat records showed that successful engagements required multiple attempts more often than single-shot kills. The human factor in accuracy deserves emphasis. Soldiers employing shaped charges operated under extreme stress. They knew that failure likely meant death, as surviving targets would immediately return fire. This psychological pressure affected aim and judgment. Training could mitigate these effects, but couldn't eliminate them. The gap between range performance and combat effectiveness reflected how stress, fear, and chaos degraded theoretical capabilities. Understanding this gap is essential to realistic assessment of weapons' effectiveness. The single-shot nature of many shaped charge weapons created tactical vulnerabilities. A Panzerfaust operator had one chance to destroy a tank before needing to reload or retreat. If the shot missed or failed to penetrate, the operator faced retaliation from an alerted enemy. This made shaped charge employment psychologically demanding, requiring soldiers to maintain discipline and aim carefully, despite knowing they faced nearly certain death if they failed. Many soldiers found this level of stress difficult to manage, affecting their combat effectiveness. The psychological demands of shaped charge employment were as significant as technical challenges. The shaped charge's manufacturing complexity meant that quality varied significantly between producers and even between production batches. Some ammunition worked reliably, other lots showed high failure rates. Soldiers complained of rounds that failed to detonate or that penetrated far less than specifications promised. This unreliability undermined confidence in the weapons and sometimes led to tragic results when soldiers relied on shaped charges that failed to function properly. The challenge of maintaining quality control in wartime production proved difficult for all combatants, though some nations managed better than others. Quality variations affected not just effectiveness, but soldier morale. Troops who experienced failures of supposedly effective weapons developed cynicism about official capabilities claims. This erosion of trust in equipment could affect willingness to engage in operations where shaped charge weapons were critical to success. Commanders needed to balance honest acknowledgement of weapons limitations against maintaining confidence necessary for offensive operations. This psychological dimension of weapons reliability often received insufficient attention in technical assessments. The response to shaped charges illustrated the continuing evolution of armored warfare. As shaped charges became common, armor designers adapted, developing countermeasures that reduced their effectiveness. This meant that the shaped charges period of maximum effectiveness was relatively brief, perhaps 1943 through 1945. Later, armored vehicles incorporated protection specifically designed to defeat shaped charges, reducing their game-changing impact. The weapon remained formidable, but it was no longer the transformational advantage it had initially represented. This pattern, where revolutionary weapons prompt defensive responses that restore some balance, has characterized military technology throughout history. The speed of defensive adaptation varied by nation and circumstance. Germany, fighting defensively with declining resources, emphasized countermeasures like standoff armor that were relatively cheap to implement. The Allies, with industrial superiority and offensive orientation, initially accepted shaped charge threats as manageable costs of operations. The Soviets, focused on mass production of standardized designs, were slower to incorporate protective features. These different approaches reflected how nations prioritized resources and responded to threats based on their strategic situations. The psychological impact of shaped charges, while significant, also had downsides. Tank crews facing shaped charge weapons sometimes became overly cautious, reducing their effectiveness through excessive concern for threats. Commanders sometimes refused missions in urban terrain, even when tactical situations demanded accepting that risk. The shaped charge's fearsome reputation occasionally created paralysis that was counterproductive. Similarly, infantry armed with shaped charges sometimes developed overconfidence that led them to engage armor in situations where they should have avoided contact. The psychological effects cut both ways, creating problems as well as advantages. This psychological double edge illustrated how weapon reputation could diverge from actual capability. Shaped charges were powerful, but not invincible. Overestimation of their effectiveness could be as problematic as underestimation. Finding accurate middle ground required experience and good intelligence about actual weapon performance. The challenge of maintaining realistic assessments amid propaganda, incomplete information, and the natural human tendency toward extreme judgments affected how both sides employed and responded to shaped charge weapons. The shaped charge's success highlighted the continuing tension between offensive and defensive capabilities in warfare. Throughout military history, periods when offense dominated alternated with periods of defensive superiority. The shaped charge represented a sharp swing toward offensive capability, giving attackers tools to defeat defensive systems that had seemed impregnable. Yet this prompted defensive responses that restored some balance. This cycle, which has characterized warfare since ancient times, showed no signs of ending. Each innovation prompted counter-innovation. Each solution created new problems. Understanding this cyclical dynamic helps contextualize the shaped charge's significance. It was revolutionary, but not permanently dominant. It created temporary advantage that defensive innovations eventually mitigated. This pattern suggests that truly decisive weapons are rare and that technological advantages tend to be temporary. The implications for military planning are significant, as they suggest that technological development must be continuous rather than episodic, with nations needing to innovate constantly to maintain competitive position rather than relying on single breakthrough weapons. The economic implications of shaped charges deserved more attention than they received during the war. Enabling cheap weapons to destroy expensive vehicles altered the economics of armored warfare fundamentally. A Panzerfaust cost perhaps a few dollars to produce. A Sherman tank cost over $40,000. This dramatic asymmetry meant that defenders could inflict economically catastrophic losses even when grossly outnumbered. Germany's ability to continue inflicting heavy losses on Allied armor through 1945, despite enormous resource disadvantages, owed much to shaped charge weapons that allowed infantry to destroy tanks at low cost. This economic asymmetry influenced strategic calculations in ways that weren't always appreciated at the time. It suggested that defense might be more economically efficient than offense in industrialized warfare, at least regarding armor. It implied that numerical superiority in expensive weapon systems might be less decisive than commonly assumed if cheap countermeasures existed. These implications challenged conventional thinking about industrial capacity's role in warfare and suggested that clever technical solutions could partly offset material disadvantages. The full exploration of these economic dimensions of military technology awaited post-war analysis. The environmental and collateral damage effects of shaped charge weapons received little contemporary consideration, but deserve reflection. The jet's extreme temperatures started fires that sometimes spread beyond military targets. Urban fighting with shaped charges contributed to the destruction of cities, as burning tanks ignited surrounding buildings. The secondary explosions, when ammunition cooked off in destroyed vehicles, created additional hazards for civilians and non-combatants. These effects were generally considered acceptable given the military necessities, but they represented costs beyond simple military calculations that modern assessments should acknowledge. The shaped charge's legacy influenced post-war armor development profoundly. Tank designers assumed shaped charges would remain threats and designed accordingly. This led to vehicles with explosive reactive armor, composite armor specifically intended to defeat shaped charges, and active protection systems that intercepted incoming projectiles. The shaped charge thus shaped, no pun intended, the entire trajectory of armored vehicle development for decades after World War II ended. Its influence extended far beyond its immediate tactical impact, affecting how militaries thought about armor protection and anti-armor capabilities. The question of whether shaped charges shortened the war invites speculation. They certainly made Allied operations against German armor less costly in lives and material than they would otherwise have been. They gave infantry tools to contest ground even against superior armored forces. Whether this significantly accelerated Germany's defeat is difficult to determine. By the time shaped charges became widely available, Germany's strategic position was already desperate. The weapons may have reduced Allied casualties more than they shortened the war, though both effects had value. The counterfactual analysis required to assess this question definitively is impossible, leaving room for different interpretations. The shaped charge's development illustrated how military necessity drives innovation. In peacetime, the shaped charge likely would have remained a laboratory curiosity or demolition tool. War created urgent need for better anti-tank weapons, which led to rapid development and deployment of shaped charge technology. This pattern, where military requirements accelerate technological development, has characterized much of modern history. Nuclear energy, jet aircraft, radar, computers all saw development accelerated or directed by military applications. The shaped charge fits this pattern, representing science mobilized for military purposes, with all the moral complexity that entails. The ethical dimensions of weapons development appeared rarely in discussions of shaped charges, but deserve consideration. Scientists who developed these weapons knew they were creating tools for killing. Some struggled with this knowledge, others rationalized it as necessary work against evil enemies. Still others simply focused on technical problems without considering broader implications. The shaped charge, like other weapons, represented human ingenuity applied to destruction. This tension between creativity and destructiveness, between technical brilliance and lethal purpose, remains unresolved in discussions of military technology and continues to challenge societies that depend on weapons development for security. The first time Allied soldiers witnessed a shaped charge destroy a German tank, the sight burned into memories that would last lifetimes. The round struck with a flash, not the clang of solid shot, but something different, a brighter light. Then the armor at impact point glowed, actually glowed, the metal heating to incandescence in an instant. Smoke erupted from hatches, followed by flames. Seconds later, ammunition inside the tank exploded, blowing the turret completely off the hull. The turret, weighing several tons, sailed through the air like a child's toy. The burning hull became a pyre, black smoke rising into the sky. Soldiers who witnessed this stood stunned, trying to process what they had seen. Tanks didn't die like that, not from a single hit by a relatively small projectile. Yet here was proof, undeniable and terrifying, that something new had arrived on the battlefield. The shaped charge transformed armored warfare between its introduction and war's end. German tanks, which had dominated battlefields through superior design and firepower, found themselves vulnerable to weapons wielded by ordinary infantry. The Panther, nearly invincible frontally against conventional anti-tank guns, could be destroyed by a soldier with a bazooka if he could get close enough. The Tiger, which inspired fear in Allied tankers, became far less intimidating when every soldier carried weapons that could kill it. This democratization of anti-tank capability fundamentally altered how battles were fought and what tactics were viable. For German forces, shaped charges represented a defensive lifeline as their strategic situation deteriorated. The Panzerfaust in particular gave German infantry ability to contest Allied armor advances even as Germany's own tank production declined. In the desperate fighting of 1944 and 1945, Panzerfaust armed infantry inflicted serious losses on Allied armor, particularly in urban fighting where the weapon's short range mattered less. Individual soldiers achieved remarkable results. At the Battle of Berlin, German Hitler Youth members, some barely teenagers, destroyed Soviet tanks with Panzerfausts in street fighting. These successes, however tactically impressive, could not alter strategic realities, but they demonstrated how shaped charges multiplied defensive capabilities. The combat reports from these urban battles revealed both the effectiveness and the human cost of shaped charge employment. Young soldiers, often with minimal training, faced Soviet armor in close combat. Success meant survival and possibly destroying an enemy tank. Failure meant death. The casualty rates among Panzerfaust operators in urban combat were extraordinarily high, yet replacements continued to appear, testament to either courage, fanaticism, or desperation, depending on perspective. The shaped charge gave these soldiers tools to threaten armor, but it could not protect them from the consequences of such close-range combat. Allied tankers developed healthy respect, bordering on fear, of shaped charge weapons. Sherman tank crews, aware that their vehicles' armor couldn't protect against Panzerschrecks or Panzerfausts, avoided situations where they might encounter these weapons. Urban terrain became particularly dreaded. Cities offered countless hiding places for shaped charge teams, and engaging them was extraordinarily difficult. Tank commanders learned to demand infantry support before entering built-up areas, and even then, they approached with extreme caution. The shaped charge had made tankers vulnerable in ways they hadn't experienced earlier in the war. The transformation of urban warfare deserves particular emphasis. Cities that had previously been objectives to capture became hazards to avoid when possible. The tactical advantage shifted toward defenders armed with shaped charges who could engage from concealment at close range. Attackers needed overwhelming force, particularly infantry support, to clear urban areas of shaped charge-armed defenders. This influenced operational planning, with commanders routing advances around cities when feasible rather than through them. The shaped charge had fundamentally altered the urban battlefield in ways that persisted long after World War II. The visual effects of shaped charge impacts continued to shock and awe soldiers throughout the war. Each occurrence seemed to defy understanding. How could explosive make metal glow and run? How could a relatively small projectile blow turrets off their mountings? The explanation involving jets of superheated metal plasma and hydrodynamic penetration was beyond most soldiers' technical knowledge. Even when explained, the phenomenon seemed more like science fiction than science. This gap between visual reality and comprehension led to descriptions that emphasized the supernatural and inexplicable, hence references to witchcraft and magic. Veterans interviewed decades after the war still spoke with wonder about shaped charge effects. The visual memory remained vivid. The flash, the glowing metal, the explosion, the burning wreck. For many, these moments represented some of their most intense combat experiences. The combination of danger, technical marvel, and visceral destruction created memories that resisted fading. This lasting psychological impact suggests that shaped charges influenced soldiers in ways that extended beyond their tactical military effects, shaping how veterans understood and remembered their wartime experiences. Engineers and scientists who developed shaped charge technology rarely witnessed their weapons' battlefield effects, yet they had created something that soldiers found almost beyond belief. The disconnect between laboratory and battlefield characterized much of wartime weapons development. Researchers working on shaped charges conducted careful experiments, measured jet velocities and penetration depths, refined cone geometries through systematic testing. Their work was methodical and scientific. The battlefield manifestation of their work was violent, spectacular, and emotionally overwhelming. This contrast between the creation and employment of weapons reflects broader truths about how technology is developed and used in warfare. Some scientists involved in shaped charge development later reflected on their work with mixed feelings. They took pride in technical achievements and in contributing to Allied victory, yet they also recognized that their calculations and experiments had produced weapons that killed thousands. This moral complexity, inherent in military research, affected different individuals differently. Some saw their work as necessary contribution to just cause. Others struggled with the implications of creating lethal weapons. Still others focused narrowly on technical problems without engaging broader ethical questions. These varying responses illustrated how scientists navigated the moral challenges of weapons development. The Germans, despite their early advantages in shaped charge technology, ultimately could not leverage it to strategic advantage. The weapons gave them tactical tools that inflicted losses on Allied forces, but they could not compensate for overwhelming Allied material superiority and Germany's collapsing strategic position. Shaped charges destroyed thousands of Allied tanks, but the Allies simply produced more tanks. Each Panzerfaust success represented a tactical victory within a strategic catastrophe. Germany's ability to innovate and produce effective weapons persisted even as their capacity to affect the war's outcome disappeared. This inability to translate tactical effectiveness into strategic success illustrated limitations of technology in warfare. Clever weapons could not compensate for industrial inferiority, strategic overextension, or failed grand strategy. The shaped charge gave Germany tools to make Allied victory more expensive, but it could not prevent that victory. This lesson about technology's limitations in warfare remained relevant long after World War II, as other nations discovered that superior weapons could not guarantee strategic success against adversaries with advantages in other dimensions of military power. The Allies, conversely, used shaped charges as one tool among many in their overwhelming material and numerical superiority. Heat ammunition gave their tanks improved capability against German armor. Bazookas provided infantry with anti-tank tools that reduced their dependence on organic anti-tank guns or armor support. These weapons contributed to Allied tactical flexibility and operational effectiveness, but they were supporting players in a larger drama of industrial might and numerical superiority. The Allies would have won without shaped charges, though probably at higher cost. The weapons shortened casualty lists more than they shortened the war. The post-war legacy of shaped charges extended far beyond World War II. The technology influenced anti-tank weapon design for decades. Modern anti-tank missiles, rocket-propelled grenades, and tank gun ammunition all use shaped charge principles refined from World War II research. The armor on contemporary tanks reflects lessons learned about defeating shaped charges, incorporating composite materials, reactive armor, and active protection systems, all designed to counter shaped charge threats. The competition between shaped charge weapons and armor protection continues today, a direct descendant of the competition that began in the 1940s. For soldiers who fought with and against shaped charge weapons, the experience remained vivid decades later. Veterans describing combat often returned to moments when they witnessed or employed these weapons. The visual drama, the effectiveness, the fear and exhilaration of using weapons that gave infantry real power against armor all created memories that resisted fading. Interviews with veterans conducted decades after the war showed that shaped charge encounters remained some of the most clearly remembered combat experiences, suggesting that the psychological impact matched the tactical significance. The scientific principles underlying shaped charges, once obscure knowledge possessed by few researchers, became widespread as weapons employing them proliferated. Post-war shaped charge technology spread globally, with virtually every military developing weapons using these principles. The shaped charge became democratized not just in its battlefield applications, but in its technological knowledge. What began as classified research in a few nations became common engineering knowledge taught in military schools worldwide. This diffusion of knowledge, characteristic of military technology generally, meant that advantages gained from shaped charge development proved temporary. The shaped charge's place in military history reflects its role as a transformational weapon that altered fundamental equations of armored warfare. Like other revolutionary weapons, the machine gun, aircraft, nuclear weapons, it changed how wars were fought and what tactics were viable. Unlike some revolutionary weapons, however, the shaped charge didn't render entire categories of weapons obsolete. Tanks remained valuable despite shaped charge threats. Instead, the shaped charge created new tactical and technical challenges that required adaptation and innovation. It was revolutionary but not completely transformational, powerful but not omnipotent. The descriptions of shaped charges as weapon witchcraft captured something true about how soldiers experienced technology they didn't fully understand. To the infantryman using a bazooka or the tanker witnessing a shaped charge's effects, the weapon seemed to operate through principles beyond normal understanding. This sense of confronting something uncanny, something that violated expected patterns, characterized much of soldiers' experience with rapidly evolving military technology during World War II. Shaped charges were simply the most visually dramatic example of a broader phenomenon where technological change outpaced soldiers' ability to comprehend the principles underlying their tools. The engineers who solved the manufacturing challenges that made mass production of shaped charge ammunition possible deserve recognition alongside those who developed the theoretical principles. Converting laboratory devices into weapons producible by millions required different skills, different expertise. The press designs that formed cones economically, the explosive formulations that provided consistent results, the fuse mechanisms that functioned reliably, all represented practical engineering achievement as impressive as the theoretical physics. These contributions, less visible and less celebrated, were equally essential to the shaped charge's battlefield impact. The tactical adaptations forced by shaped charges influenced how armor was employed for decades after World War II. The lessons learned about infantry armor cooperation, about the vulnerability of armor in urban terrain, about the need for combined arms operations, all reflected responses to shaped charge threats. Military doctrine incorporated these lessons, changing how armies trained and equipped their forces. The shaped charge thus influenced not just weapons technology, but military thought and organization more broadly. Its legacy extended into institutional knowledge and organizational culture that shaped how militaries approached armored warfare long after the weapon's introduction. The shaped charge's legacy includes its role in making anti-tank capability affordable and distributable to forces that couldn't field expensive anti-tank guns or armor. This has influenced conflicts from World War II through modern insurgencies, where shaped charge weapons give lightly equipped forces ability to threaten armored vehicles. The political and strategic implications of this weapons category extend beyond tactical military considerations, affecting how states think about force structure and how non-state actors approach asymmetric warfare. The shaped charge democratized anti-armor capability in ways that continue to affect conflicts today. Reflecting on the shaped charge's history reveals lessons about innovation, adaptation, and the nature of military technology. Revolutionary weapons rarely remain revolutionary for long. Countermeasures emerge, tactics adapt, and what seemed transformational becomes another factor in military equations. Yet the period of maximum effectiveness, when a new weapon provides overwhelming advantage before defenses adapt, can significantly influence campaign and war outcomes. The shaped charge's period of maximum impact, roughly 1943 to 1945, corresponded with critical phases of World War II, magnifying its historical significance beyond its absolute capabilities. The shaped charge also reminds us that warfare rewards clever application of physical principles as much as brute force. The ability to defeat thick armor with small weapons depended not on having bigger guns, but on understanding and exploiting physics in ways that bypassed conventional approaches. This intellectual dimension of military competition, where scientific understanding creates advantages, characterized 20th century warfare increasingly. The shaped charge exemplified this trend, representing physics weaponized through engineering ingenuity in service of military objectives. For the soldiers who called shaped charges weapon witchcraft, the term conveyed wonder, fear, and incomprehension. They lacked vocabulary to describe what they witnessed because it fell outside normal experience. Armor didn't just break when hit by shaped charges, it seemed to melt, to flow, to behave in ways solid steel shouldn't. This disconnect between visual reality and conceptual understanding created descriptions that reached for metaphor and hyperbole. Yet those descriptions, imprecise though they were, captured something true about encountering technology at the edge of one's comprehension. The language of soldiers struggling to describe shaped charge effects reveals much about how humans process extraordinary experiences. Metaphors of melting, flowing, magical transformation all attempted to communicate visual phenomena that defied everyday categories. This linguistic struggle parallels earlier soldiers' attempts to describe machine guns, aircraft, or other revolutionary weapons when they first appeared. Each generation of military technology seems to produce moments where existing vocabulary proves inadequate, forcing soldiers to reach for new ways of describing what they experience. The shaped charge's story is ultimately one of human ingenuity applied to the ancient problem of defeating protection. From the first weapons designed to penetrate shields and armor, through medieval siege engines and gunpowder artillery, to modern anti-tank weapons, the competition between protective and penetrating capabilities has driven innovation. The shaped charge represented a particularly clever solution to this perennial problem, one that used physics in counterintuitive ways to achieve effects that seemed impossible through conventional means. That soldiers described these effects in terms of witchcraft and magic seems fitting. The shaped charge operated through principles most couldn't understand, producing effects that defied everyday experience. It represented science so advanced, it resembled magic to those without the knowledge to comprehend it. This is perhaps the essence of revolutionary military technology. Weapons that work through principles beyond most users' understanding, that produce effects that seem impossible, that change warfare's fundamental equations. The shaped charge achieved all this, earning its place as one of World War II's most significant weapons innovations and its reputation as the round that melted German tanks like butter through what soldiers could only describe as weapon witchcraft. The metaphor of melting deserves final consideration. It captured the visual reality soldiers witnessed while conveying their sense of transformation and violation of natural order. Solid steel doesn't melt from impact. Yet that's what armor struck by shaped charges appeared to do. This apparent violation of physical law, this transformation of the solid into the liquid, carried almost alchemical significance. The shaped charge seemed to transmute materials, changing their fundamental nature. For soldiers witnessing this transformation, the metaphor of witchcraft and magic was perhaps the only available framework for comprehending the incomprehensible.